at the both of you.
I'll just take a second to introduce you. I have my handwritten notes with wrong universities, but nevertheless, yeah. So there are a couple of people coming in. Okay. Good afternoon, everybody. Very happy to welcome our colloquium speaker today, Dr. Girish Rao. So Girish has spent his career looking at how principles of colloid and interface science can be applied to the real world. So at present, he's a professor of practice in IIT M. He teaches courses at IIT Tirupati, and his research interests right now are carbon capture and renewable energy sources for fishing villages. I hope you're going to tell us about that today. So Girish did his PhD in Imperial College London, a postdoc in UCSF, where he worked on making glucometers. And then he was in Hindustan Lever working in the detergent department, and he's the one who's responsible for the plastic coating on Vim. So I hope you tell us about that too, and the look of the Pierce soap. I think, yeah, there is a coating on top. Yeah. And after that, he was in Shell, where he worked on the corrosivity of amines and on asphaltenes and nano-aggregates.
I'm not clicking it.
Is everything okay?
Yeah,
okay.
now.
Okay. So Girish, over to you.
Okay. Yeah, I was having the usual IT issues, but hopefully that's been solved. This visit is actually very long overdue. You can hear me? Yeah, because not only because I've been in Bangalore for 30 years and not visited until last November, but there is, of course, also a professional link. As you said, I was with Unilever, and in fact, one of the first people I recruited in Unilever was someone called Rajesh Ganapati, and he worked in our team for about a year, saw the light, and came to RRI, where he worked with Professor Sood, I think here. And I think he's a professor down the road, correct me if I'm wrong. And of course, with Unilever, where I was, where sort of my formative years, many collaborations. I think Sudipto, who's a close friend of mine, has done some collaborations with Ranganathan, Professor Ranganathan as well. So that story continues. So professionally, I should have come earlier. But there's also a social connect, believe it or not. Many of you will know, or at least might even have visited the Raman bungalow in Malleshwaram around the corner. If you'd visited 50 years ago, apart from you and me, not many people in the audience would know about it, and went around the corner, a bungalow was there, and that belonged to my grandfather. So my grandfather and Raman were neighbors. My grandfather was also a scientist, not as illustrious as Raman, of course, but he was the head of the chemistry department in Central College, and principal there. I think he was the first Indian principal. And then he was the HOD in P&I, Physical and Inorganic Chemistry in ISC as well. So better late than never is what I'm going to be saying for me to visit here. It's a fantastic place from what I've seen, and I'm still trying to absorb all what I've seen over the last few hours. But what I hope to share with you over the next 40 minutes or so, and hopefully there'll be some discussion time, right? So I really hope I can trigger some points of discussion, because something I'm quite passionate about, you might even say activist, is around energy and climate change. Especially over the last few years, where I've started doing more and more teaching, one of the questions I've asked many students and even faculty, believe it or not, is, of all the countries on the planet, which ones do you think will be most impacted by climate change? And quite often the students and the faculty will say it's those small islands in the Pacific Ocean, which, yes, it's true. They're only 1 meter above sea level, and if sea level goes up, they will disappear. And that's, yeah, no doubt about that. But very few of you say India, and that shocks me. Yeah, it really shocks me, because our current thinking is this. Any country which has an economy which is sort of based still, even though we're changing, our economy is still very much agriculture based. Yeah? Agriculture, I think, is still around 50% of our GDP. If monsoon fails, our GDP will drop, yeah, and we will struggle. And monsoon failing means what? It doesn't mean just having the total amount of rainfall. It has to rain at the right time, in the right place, at the right amount. Yeah? And as all of you will know, it's beginning more and more irrepeatable every year. This year, I don't think it stopped raining in Bangalore until November. Yeah? So this sort of thing is not good. Yeah? On top of that, we're a growing economy for the other parts where most of our fuel is still, unfortunately, fossil-based, coal-based. Yeah? And there are reasons for that. I'm not saying we shouldn't, but that's worrying. Yeah? Because if our economy needs to grow, we need more energy. That means we need to somehow figure out how to provide those joules of energy without generating tons of CO2. Yeah? And so in our opinion, ours meaning not me only, but many colleagues in Shell, the idea is, well, we're in trouble. Yeah? India is one of the worst probably impacted countries to climate change, and we don't talk about it enough. We talk about it a bit about Russian oil, this, that, and the other, but really we need to try and do some other things. So I'm just going to spend a couple of minutes on that. And then, of course, the final thing is, yes, even if you have the technologies, it would be a very, very brave politician to suddenly flick a switch and say, we're going to stop coal, oil, and gas, because the number of people Coal India employs is huge. Yeah? And one of the biggest customers for Railways India, which is an even bigger employer, is Coal India. So if you suddenly flick a switch and say no fossil fuel, how are you going to provide employment for that huge population? It's not like in the West where you're talking tens of thousands. Here we're talking hundreds of thousands, lakhs of people who will be negatively impacted potentially. And that's what I'm just going to touch upon over the next 5 or 10 minutes. So I'm a chemist, as Ranjini said. My view of the greenhouse effect is I try and keep it as simple as possible. The sun is hot. It's a hot body, black body. And what the physicists tell us, black body radiation, at that temperature, you're going to be hitting us, the planet, with UV-vis frequency of radiation. Yeah? The atmosphere, as we know it at the moment, doesn't really have a huge impact on that incoming radiation. The Earth is much cooler, fortunately, and hence it irradiates in the IR region predominantly. So that radiation going out is what I would call a cooling flux. Yeah? You're trying to cool down the planet. As it is coming from radiation, the Earth atmosphere, unfortunately, or fortunately I should say, contains molecules which interact with that IR radiation. For those of you who are spectroscopists or chemists, we learned this very early. That equation you see down there is something we would call the Beer-Lambert law. And basically what it tells you is as the concentration of those IR-absorbing molecules in the atmosphere goes up, the amount of cooling will go down because the amount of transmitted radiation goes down. And that's the very simple way I look at it. It's, of course, a lot more complicated than that, especially when you're trying to predict monsoon and this and that. Much more complicated. But to a first approximation, this is the problem. That CO2, concentration of CO2 in the exponent there is going up, and we'll touch upon that as well. But it's important for you to know this because, unfortunately, there are politicians and people in the world who don't believe this picture. Yeah? And as scientists, it's easy to say we failed, but we haven't done a great job of explaining something simple and deadly to those disbelievers. And it's very important that you do, and you act as a role model in explaining, or at least challenging those of us who believe in this model. Yeah? At the moment, I'm not getting that dialogue. People will just say, I don't believe, but they won't engage in a discussion. But it's very, very important to understand the first level of physics and chemistry. The next 2 slides are scary slides, from my opinion. What is the size of the fossil fuel market. I'm from industry, so we always look at dollars, yeah? And the energy market, these are approximate, is trillions of dollars. This is global, not India, but India, it's big, right? Trillions of dollars, and that results in millions of kilowatt hours, or trillions, sorry, yeah? Lots of energy, yeah? So, as I said before, it is going to be very, very difficult to replace those trillions of barrels of oil at a flick of a switch to something much nicer. But we have to do it. How we're going to do it, I'm not sure, and that's what we have to discuss. The other thing I want to mention here, and that again, many of the people don't discuss that much, is the time it takes to get to this scale. My sister laboratory in Amsterdam, Shell, was born 100 years ago. So for 100 years, we have been focusing on how to produce oil, explore for oil, produce oil, refine the oil, generating all those lovely products that you will be using. 100 years, yeah? I guess there aren't many groups, let alone companies, who have spent 100 months working on the same aspect or a deeper aspect of renewable energy. But somehow we have to do that in that sort of speed of time, 100 months, yeah? And I'll explain that in my opinion, how we have to worry about 100 months, not 100 years, yeah? The transition, this is the controversial part, this is my view, is that because you can't flick a switch, we need to come in a phased manner, you know, fossil fuel going down, renewables going up. It's controversial because many people will think the money we're investing still, unfortunately, in oil and gas is money we should spend investing in renewable. And that's really hand on heart, that is a valid googly. But we can't do everything. And so I think what we're trying to do in my earlier employer is reasonable, because we also have to meet something called shareholder value and stuff like that. We can discuss that in more detail if you want. But this is why we have a massive challenge, yeah? And I wouldn't be too worried about it, because many people think we have a fair amount of time. Before I joined Shell, I thought it's something really only my grandchildren would need to worry about, right? Yeah, unfortunately, it's not quite that nice, yeah? So there are some tipping points you might hear in the media. We're talking about we have to keep this delta T here is the temperature we are today compared to the temperature before the industrial sort of revolution started. So we're talking about 100 odd years ago. And the modelers and the politicians and the economists say we have to keep that 1.5 degrees centigrade, otherwise things are going to go bad, yeah? Now, hopefully you know what COP30 is. Many people already across the planet are thinking we've crossed 1.5. If not 1.5 already, maybe in a few months we will hit it. And so the next thing people are worried about is 2 degrees centigrade, because when you put in the models, what is going to happen after 2 degrees centigrade, things really, really go bad, yeah? So everything we're seeing now, we are just blaming on Mother Nature, but actually it should be blaming it on us. Maybe you can blame it on Shell, but we're all using our products, oil products, unfortunately. And when we think about that, we're pumping, this is the planet, 37 gigatons of CO2 into the air, okay? That's a lot of CO2. Plants and everything only use up net effect or 4 GT, yeah? So you don't need to be a chemical engineer to figure out inflow of mass is 37 GT into the atmosphere, and we're only sequestering effectively 4 of GT. What's happening in the CO2 concentration? It's going up. And that's why they think we're going to hit 2 degrees centigrade, not in my grandchildren's time, but hopefully even in my time. Well, not hopefully, but this is the speed we need to get to. And that's why it's so, so important that people in this room and in all the academia, we start worrying about it, yeah? So the real irritation I have, okay, the students and the faculty who I've spoken to didn't know India was going to be impacted. Then you explain to them, and then I ask them, well, who's going to solve this problem? They point to the West quite often, yeah? And I find that disappointing, because the West isn't that impacted. it's India which is going to be impacted. So there is a driver, of course, but the solution has to come for us. It's not going to come from Europe. And currently with Trump, I'm not sure if America will be that into it. So let's try and solve these problems ourselves. And that's one of the reasons I'm giving this sort of monologue on the subject. So please do read about it. Do challenge us, for those of us giving this side of the story, and take it forward. You had a question? Net land. Yeah, unfortunately, CO2 is not quite as soluble as I would have liked. You know, if CO2 was soluble, the sea would suck it up. But the models are showing we're really getting to that limit. And what you will find is, unfortunately, as CO2 dissolves, the pKa of bicarbonate is 6.4. So the sea is getting more acidic, and you'll read about the coral reefs in Australia getting bleached, et cetera, et cetera. It's getting more acidic. So we're not really going to be able to leverage the sea much more than we have already. Yeah, that's the thinking. But but it is important. The 4GT, I said net. It's important to remember net. What certain people, politicians say is, in fact, if you just look at how much CO2 plants suck out, it's actually orders of magnitude of bigger. Yeah. So everyone's saying, no, we're fine. The problem is plants also respire, right? So the net effect of photosynthesis versus respiration is much smaller. Yeah. So please remember that googly when somebody comes to you having listened to someone saying there's plenty of Amazon for the planet. That's not what we think. And the way the Amazon's disappearing, and they're burning some of that. So they're burning it, so all of that is going into the air without generating energy for us. So it is very scary. Yeah, so please do ask more questions or worry about it. Okay, shift to what I'm supposed to be talking about, which is about soft colloid matters. And so I was thinking about how best to shape this presentation. And one way I do that is by giving you case studies of my experience. It's based on real events. I didn't want to give the exact details because then I'd probably have to go to Shell and Unilever and say, I need legal approval. So I've done it this way. There's nothing confidential in these case studies. So I've got 2 case studies. Both of them are from the oil and gas industry, but the physics is also relevant to Unilever as well. So the first one is a sort of email that I used to get, unfortunately, nearly always on a Friday afternoon, just when you're packing up, hoping to enjoy your weekend. You get a mail from this, and I'll go into more detail. But basically, we designed a surfactant formulation to help clean the rock to improve the amount of oil coming out when you produce oil. So oil sits in rocks below the surface. We designed surfactants to clean it out, and they're expensive. We sold those surfactant formulations, and the customer came back to us and said, actually, your expensive surfactant solutions were actually generating less oil than cleaning with water. So it's a bit like having a Surf Excel bucket, which you've paid 30 rupees for per whatever, and finding out the detergency is less than just washing it in water. Yeah, you would not be happy, and that cartoon there is really what that customer was not happy about. We had to figure out what happened to that. So to explain how we resolved this or understood what happened, we need to sort of go back to some basics. And I know there's this perception everywhere that fundamental science or understanding is not needed in industry. So I'm going to try and break that myth. I might pass, I might fail, but there is a lot of fundamental stuff, or at least understanding, that we have when we design our formulations. So the first thing I do when we teach new scientists and engineers who joined Unilever and Shell was this, when we're talking interfacial science. Yeah. So let me explain the experiment. The experiment my ancestors did way back in the 60s, old even by my standards. They took some oil and added it a drop by drop into water and measured the calorific, so the heat. Yeah. Now normally when you have molecule A and molecule B, they like to mix. It's what we call entropy of mixing, yeah? And you can calculate what we call a delta S function, that is entropy, change in entropy. When they did these experiments, they found that the entropy change going from oil into water was acting against them. Yeah? So instead of entropy of mixing normally driving a mixing process, the entropy change was actually going against it. Yeah? And much discussion was there for many people, but basically the thinking, even now, as I understand it, is you have a hydrocarbon shell. I know most of you are physics, so I'm going to try and not talk too much chemistry, but you'll have a chain, and when that gets solvated by the water, it has a layer of frozen water molecules. Yeah? So basically, when that hydrocarbon chain goes from its hydrocarbon phase into water, you have this very, very structured water layer around it. Yeah? And that is a very, very low entropy system. And hence, you get delta S going in the wrong direction. And this is what we think happens for surfactants. Yeah? We think surfactants can go to oil, and I've drawn it. The surfactant here is a red circle is what we call the head group, and the black is a tail, which is it likes the oil, oleophilic, and they stand like this, and basically those tails now are hiding from water. And so that structured water layer that I showed you in the earlier cartoon gets released, and it's entropy driven. Yeah? So it's an entropy absorption process. Of course, enthalpy plays a role. How does that hydrocarbon tail interact with the oil? But we think a lot of this is entropy driven. Similarly, for self-assembled structures, which we call micelles, a strong driving force for that is, in fact, the hydrophobic effect, where you can measure what we call the CMC as a function of temperature, and you'll see it's not that temperature dependent. And that's a clear sign that it's not enthalpy driven, it's entropy driven. And so this system, even though it looks more organized, is actually much more disorganized than the system on the left with a monomer. Non-intuitive, but that's what we think is happening. To really understand it, you need to know the structure of liquid water, which I don't think we really know that well even today, though protein folding and AI/ML has sort of made changes in that. For the students, there's a fantastic book, if you've not already got it. Israel is sort of the Bible for many of us who started in this field, and I strongly, strongly recommend it. So he will explain a lot of things of how we design surfactant interfaces, and that's what we do even in the detergent powder you buy in your shop. So you have oil and water, yeah? And I'm going to draw my hydrophilic surfactant as a triangle. My hydrophilic, using the language of a chemist, means you've got a big base, because it likes the water, and a thin tail. It's not that oil-loving, and that's what we call. So it has that shape. So over here, you'll see there's quite a lot of surfactant at that oil-water interface, but there are also quite a lot of empty spaces, yeah? I've tried to pack the surfactant as close as possible to the oil-water interface. So how do we actually lower that interfacial tension? We try and maximize the amount of surfactant there. So you grab a surfactant, which is the inverse of that triangle, what we would call a hydrophobic surfactant. And now you see the picture on the right is very different. Yeah? Now we have surfactant filling in the gaps at the interface, and you have significantly lowered the interfacial tension. These shapes, Israel describes it very elegantly based on thermodynamics. So it's not just a chemist waving his hands to do this. There is some physics there behind it as well. And basically you get to very, very low IFT measurements. And that's what's there in your Surf Excel or your Procter & Gamble. I'm a still loyal Unilever person. So, and we mix non-ionic surfactant with LAS, which is like your SDS, and generate that formulation. The first formulation we had was with a very hydrophobic surfactant. It had a very small head, and it worked beautifully. Yeah? Unfortunately, because it's water insoluble, it was not allowed because things will accumulate in the water So the water table gets these surfactants in there, and if they're oil soluble, not water soluble, they'll build up in the fish, and you'll see it's not allowed. So we moved to a EO7 system, and especially if you buy XL Matic for front-loading machines, that's in there because it's also got a poor profile.
Just to understand the mechanism, so it's the surfactant loving back to the so the idea is to remove the oil from your
Yep.
yeah. So how does this do it?
I will show you. Yeah. What I'm going to first try and do is show you how it happens and then the physics. Yeah. Because it's you're hit the nail on the head. All right. For resolving that case study. So something Unilever was really good at are these educational series. They have some really nice pamphlets, and this video is part of that. So unfortunately, it doesn't have audio with it. It had when it was an analog. It's a very old video. Yeah. But what I'm hoping to show, especially for the person in the back, a lot of it is based on microscopy, and it's really elegant, and I'm hoping you'll see that imaging is science as well as artistry. So what we have in Unilever, and Procter's will have it as well, we'll have a whole bunch of labs, not full of lovely microscopes and IFT and tensiometers, but full of washing machines. Yeah? And that's our bread and butter. Yeah? So this is how we understand what's happening in detergency. Then I'll explain a bit about the physics in a bit more detail. It's only a 5 or 6 minute video. So this is the lady who's showing the video. This was from the Dutch laboratory in Rotterdam. So look at the equipment. It's when you can show the date, but good old-fashioned microscope. In those days, the cameras were these big CCD, and they were expensive. So what you all have here is, what you have on your phone is much better than this. But basically, we would look, this is Piet van der Vlist, unfortunately no more, but he would put soil onto cotton and look at it under the microscope. So this is how you would do it. The red color is because it's a bit like Navratna Tel. We add a dye so that you can see it in the microscope. And this is a picture, the cartoon of how clothes get cleaned. There are two fabrics we look at. One is cotton and one is polyester. And so this is when you've added surfactant, you see it all coming out. You'll see some oil droplets there or even skin cells which are not coming off. So here, this is where it starts getting interesting. You take a polyester fiber, you can tell from the contact angle and things coming off at the top and it rolling up. So the contact angle is changing with time because of the surfactant. And I'll explain what I mean by contact angle and stuff. So, and convection is needed. So you can't wash your clothes, as you all know, without a bit of action. Yeah, that's the action. So this is a polyester film. Same vegetable oil, which is the standard oil you'll have in our foods. And again, you see how slow it is. It's a bit painful. But after some time, it does roll up and come off as a drop, if you've got everything going the right way. Skin fat, very, very important. So the collars, which you'll know on your shirts, that's this horrible beast. And to get it to come off, you'll see emulsification happening as well as roll up. Yeah? Surfactant action is needed to help roll up, and mechanical action, convection is needed. So beating your clothes with a bat, it has some physics to it. Yeah? You can see at the top that there's some emulsification happening there. All sorts of Marangoni type stuff happens in the real world as well as the oil starts disappearing. What would the scale bar be for that? Oh, it's big. by your standards, this is 1980s science. So we're looking at it with just a standard goniometer. It's not, it's quite big. All right, this is where it gets interesting. Phase diagrams, which we all love and hate. Liquid detergent, oil, water. What we'll be doing is, if you start off at different points in the phase diagram, how does it change the cleaning? Yeah? Remember, this is 1980s type imaging. And we start off with a system which has a fair amount of detergent, and it's quite heavy in terms of concentration. You'll see what happens. So this is dirty motor oil. You'll see a fair amount of oil and a liquid detergent, but the oil is in excess. So you get cleaning, pretty good cleaning, yeah? Not bad. Now look, 1:1 now. So we've increased the surfactant and it blows up. So this is where your IFT, your interfacial tension, has gone from plus 0.12 to virtually 0. So these are what we would call microemulsions. These are emulsions which are thermodynamically stable. So that interfacial tension penalty is more than off-balanced by the entropy of mixing, yeah? Because the interfacial tension is nice and low. So it will stay stable forever. So you can see why we've had generations of engineers doing the Navier-Stokes solution near the interfaces. Everything is changing. Your surfactant has to come and absorb at that speed. The reason you need high concentration is to keep the IFTs nice low. For the sake of time, we play with temperature and salt to change the shape of the surfactant. But I can leave this video with you if you're interested. So now let's go back to the original question. How does EOR work? So instead of cotton or polyester, you have a rock. The red circle is an oil drop, and it's immersed in water. Yeah? There are essentially two mechanisms. Third one we'll ignore. One is what you saw in the video, the stabilized oil drop. Yeah? So it's a surfactant comes and adsorbs at all the interfaces, because it's not clever. It goes everywhere it likes, and removes the oil drop. And the other one is the emulsification route, where you just have smaller drops. But the oil-water interface is incredibly important. We've had generations of physical chemists defining surfactants, designing surfactants which minimize the oil-water interfacial tension. And we do that by looking at the contact angle. So what I've done there is the red drop, where it's contacting the solid and the aqueous solution, is what we call a contact angle. And if you drop F2, which is the oil-water IFT, to 0, you'll notice it will make theta such that the drop becomes an oil drop, right? So this is what we think was happening in the lab. We'd put that red oil drop. We got the rock from the customer. So the customer sent us, this is the rock we think is below land. This is the crude oil we think is below the surface. And so we did experiments like this, where we designed our surfactants such that gamma water oil wasn't close to 0, a bit like you see in the videos. And that's because then we saw the contact angle and the thing dropping off. So we sent the customer pictures and data not only of the clean surface, but of the IFT. And this is what got us the contract. They said, great, we think we can make lots of money out of this. So then, when they came back to us with data, which was clearly showing our system is worse than water. So we had to sort of think, what did we do wrong? And the answer actually is, unfortunately, 12 standard physics, quite different. So they sent us, as a chemist, I would say hydrophilic carbonate. So the contact angle started off, in the way I've drawn it here, less than 90. So the rock preferred to be wet by water. Yeah? So when you reduced gamma water oil, you got excellent cleaning. The rock, which was actually underground, was actually what we would call hydrophobic. So you noticed in this case now, the rock prefers to be wet by oil, not water. That simple change, if you drop gamma water oil now, you get it to spread. So instead of coming off and cleaning, it was actually spreading and lining my rock with oil. And that's why we got hardly any production, because the rock preferred to be wet by oil than water, thanks to our gamma water oil changing. So it's quite irritating, and it led to, obviously, a lot of finger pointing. We did have a fantastic formulation in terms of gamma water oil. We were able to push back saying, you sent us the wrong rock. But we should have been a bit more chalu about how we developed it, because we knew cotton and polyester, quite different detergents you get from them both. We should have known with these sort of systems and the oil that they did send us, you have the running the risk of this. And you can do these experiments at home. You take your non-stick Teflon system and see how water spreads and oil spreads in the presence of surfactant solution. And if you have an oil droplet and you cover it with surfactant solution, you will notice the oil droplet, which is in air, rolls up, but in the surfactant solution it spreads. And that's what we were seeing here. Yeah? So as I said, understanding theta, all these different surface energies, that's something we do very regularly. One of the first experiments I did was I drop a surfactant solution, you can do it here, on filter paper, and you see the speed at which it spreads. Yeah? Very easy experiment to do. Very easy experiment to do. So you do it with water and it spreads at a certain speed. And then I did it with surfactant solution. And it actually spread slower, which was a bit non-intuitive for me, because I was expecting theta to go down. Because we know surfactant adsorbs at the water air. That's why you have nice soapy foam. We know it adsorbs at the solid water. And I didn't think surfactant could go ahead of the meniscus into the air and adsorb at the solid air interface. So my conjecture or hypothesis was that the surfactant was sticking down, head down, and sticking into the water phase. But this is where fundamentals come in. When I went to my boss at the time and said I have a surface excess, which was increasing IFT, he gave me a blasting. He was old school, because if you have a surface excess at any interface, the IFT has to come down. That's Gibbs. J.W. Gibbs has said it's a Gibbs absorption isotherm, and I was claiming to violate it. So it was interesting, but we didn't get any further than that because it was a fundamental interest. I do think it has scope for exploration. I think we can do some work here because it's relevant to flotation. They talk about hydrophobic surfaces, which I don't think is, we don't know why it seems to work. Anti-corrosion agents, very, very important in industry, where instead of it being cotton, it's steel, carbon steel, and hair conditioners, or fabric conditioners, where you have cationic adsorbing on negatively charged surfaces. So can this happen or not? We still don't know. The other application, it's a very simple experiment you can do, and you might have seen it in your labs who have electrochemistry stuff. If you put a salt solution in a beaker, so that beaker at the bottom there, and you just fill a small amount of it up, and you keep it under conditions of low RH, temperature is not that important, but low RH, and you allow it to dry. Very simple, just allow it to dry. What you will see is the salt goes up the sides of the glass and goes round the other side of the glass. So the salt you can see on the outside of the glass. So how has the salt gone from the inside bottom part of the cup, the glass, all the way up and around? Is thin film physics, which nobody they've looked at it for many years. We've not really understood how it works. So what is happening, the picture there, the red dotted line, is you're getting salt migration and precipitation ahead of where the water was in the first place. Yeah? And we don't understand that at all at the moment either. So I think this has, it's called efflorescence in the cement industry, and it's bad for this is the picture on the left. It's called efflorescence in the soap industry as well, so Unilever should still be interested in. And wherever you have salts and materials of construction, green hydrogen electrolyzers and membranes might also be worried about this. The final one I'm going to go through very quickly is the second case. A ship got stranded at Mangalore airport, get an email saying a ship came in, our distributor cleaned it out with a solvent, then added some of the fuel oil, which we sent them, and it started to precipitate. Yeah? And then we said, well, that's not quite right. What will happen? They said, we'll add more solvent. Because something's precipitating, best way is to redissolve it, add more solvent. They did that, and they got even more precipitation. Yeah? And they couldn't figure out what was happening. Let me explain to you why it's happening and the mistakes we made. And we were able to fix this one, though it did come at a cost. So first of all, what is fuel oil? A picture over there, crude oil, just in case you aren't aware of how you get all those lovely products in your home. Crude oil comes into a refinery. You first distill it with atmospheric distillation, and then it goes, we take the bottom part of that cut. So the black, there's something called long residue. So the bottom of the barrel of that distillation column, you'll see goes to the vacuum distillation column. There we do the distillation but under vacuum, and we get something called short residue. It's the black sticky stuff which we put on the road. It's called bitumen. Yeah? We can also mix it with all sorts of solvents and put it into a ship. And that is what we call fuel oil. That is responsible for gigatons of CO2 every single year. Okay? And there's something called the International Maritime Organization, who are going to try and make the CO2 footprint less for fuel oil. But a certain country said, whoever signs that, we will put tariffs on them. Yeah? So it's struggling because these are big polluting systems. And we have to somehow figure out how to replace that very large volume, low margin product. We don't know how. We have some ideas, but we haven't solved it yet. So what is fuel oil chemically? You're all physicists, so I'll keep it simple. You have part of fuel oil, which is actually this molecule here. It's a generic, what we call asphaltene, and it's a colloidal particle dispersed in what we call the maltene phase. I'm not going to go into more details, and the system is based on that. For those of you who are into rheology, these asphaltene phases form gel structures. Believe it or not, that bitumen you see on the road is a gel structure. So when your wheel goes over the bitumen, you apply a force, but it recovers. So it's a viscoelastic road, we call it, flexible pavements. So there's a lot of beautiful physical chemistry and colloid chemistry in this beast, which we've used a lot in bitumen, which is useful for the bitumen, but a pain in the backside for our friends in the fuel oil. So we know it's difficult because this asphaltene precipitates, and that was causing the problem. So before we actually send things out from our refinery, we test it for stability. The stability is a very simple test. The red circles are asphaltene, blue is the maltene phase, and you start first adding what we call aromatic solvent. Toluene, a good example, yeah? And you keep everything nice in solution, and then you add cetane, CHC10, and that's saturated. That's not aromatic. And at some point, you've made your blue phase not sufficiently red, and it precipitates. Yeah? So this is a test we do. We do it all the time in the labs of refineries and R&D centers. So what you get is what we call a spot test. At the start of the titration, you get what this picture is on the left. You keep adding your non-aromatic solvent, and you get a ring, a bit like your coffee ring. Yeah? And you know how much aromatic solvent you've added. You know how much cetane you've added. You can figure out a value called the p-value. So by doing what we call, well, the thermodynamics is very pretty and elegant. Don't want to talk too much about it. But based on all of this, we calculate a ratio called the p-value. If that value is more than 1.5, system is stable. If it's less than 1.5, you're in trouble. Yeah? And we did the test in our refinery, and our distributor, who before he put it into the ship, had also done it, and he also got a value of 1.5. So what did they do such that it precipitated in the tank? Yeah? What they thought was a solvent was in fact an anti-solvent. So they cleaned out our tank with cetane, yeah, or with kerosene. Yeah? Kerosene is not that aromatic. And hence, when you added your fuel oil, it precipitated. Then they thought, let's add more kerosene because it should redissolve. It's a solvent. That just made it even less stable, and your system precipitated. So that's what we figured out. The problem was we had told them to use any old solvent to clean the tank. Yeah? Don't worry about it. We should have been more explicit. But we were able to clean up the mess, literally, by adding aromatic solvent, toluene. We paid demurrage costs, so those of you, the tank was stuck there in Mangalore for a few days. That's a huge cost. And government of India are not happy with us. But we were able to sort of solve it. But we were able to get it back into solution by understanding how that SOP works. Yeah? What is the opportunity for doing this? Fuel oil and bitumen, there's not much scope for innovation. We've been doing it, as I said, hundreds of years. Biorefineries are coming out. Biotar is very similar to the asphaltenes. And I'm convinced, having the sort of test we use for fuel oil for the biorefinery, using the capabilities that you have, is possible. Yeah, we should be able to do it, especially with what you have. It is also, according to Copilot, a novel idea. Yeah? Normally, in mature industries like oil and gas or FMCG, you ask an idea, it's always been done before. But in this case, since biorefineries are so new, they will need to be able to characterize their feed, diagnostic test, to figuring out how stable is their system. So this is another opportunity that you already have capabilities for. What I'm trying to push here is that what I've seen in November when I visited and what I've seen today, you have capabilities you can apply immediately. Yeah? We just need some sort of a good discussion with industry. If I can find 2 or 3 opportunities in one visit, what is all that waiting to be unpacked by you guys is incredible. And what the equipment I saw, from NMR to the AFMs to SEMs, is amazing. And I think that, so it would be nice to have some small projects, not big ones, without sacrificing your expertise. And as a leader, from my industry experience, I know when we had a project for improving the F1. F1 is in motor racing. Shell used to sell the bitumen for those roads. So that was also, it was okay. But as soon as I got my team to work on village roads for India, their morale and energy levels went up because they could see it helping the planet. And I would really, I think for junior people, knowing how measuring that contact angle or that drying pattern or that force distance curve is going to translate into something is something you can really, really do very easily. Thank you. So I'm hoping there are questions.
Yes, I'm sure there are questions.
In the oil stuck to the rock example, so how do you recuperate the oil later? Let's say.
Yeah. So oil-water separation is a bit of a nightmare. Yeah. And it's not done easily, especially when you have surfactants in there. For normal oil production, it's painful, but it can be done. And you just allow good old-fashioned physics to help you. So you just give it a bit of time. They have sort of electrical systems to help. Sometimes we have demulsifiers. So companies sell you expensive surfactants which help separate, right, by Marangoni flows and this, that, and the other. Now, chemical EOR is not flavor of the market at the moment because it's only really viable when oil price is above 90, 80, 90, yeah, when you think about it. So even though we messed up, it wasn't a very costly mistake because oil price, as you know, is around 60 at the moment. So they're not looking at it too much. Another area where colloid science is incredibly important is, since you were in Canada, you said? Yeah, so oil sands in Canada. That's where you have this bitumen sand, which has all this heavy oil in it. And then they wash that sand. So what do we do with that sand? They just put it in huge tanks and let it sediment. And yeah, that takes a long time, a lot of controversy about that as well. You would have heard in Athabasca that the cost of that washing of that soil is extremely expensive and CO2 intense. But that's where you have a beautiful, you were talking about clay, the mud settling. The physics is that exactly. But these things are stable for too long. It takes years. So they call it tailings ponds. So it's all colloid science, in my opinion. I'm biased, but in my opinion.
A couple of questions. First one is, what is biorefinery? I have not heard of this before.
Oh, good. I should have said that. Biorefinery, we hope, right? It's not really there yet. India's beginning to do it. But instead of crude oil, you send all your bio waste into this big refinery. And instead of cracking crude oil, you crack all the bio waste, you digest it, and you generate exactly the same cuts. Not exactly the same, but you will have kerosene coming from bio rather than from crude oil. Benefit, bio is in theory net zero-ish, yeah? So because, as you said, all the carbon that is there in a plant has come from sun, from photosynthesis. So net is around zero. It's controversial. Issues with that, of course, is getting the supply chain working. But it's something which we're very excited, well, I won't say excited about. We're looking into it. India's looking into it. And again, I should sort of give you a flavor for the numbers. A plastic bottle, a PET bottle, yeah? Each ton of that generates about 4 or 5 tons of CO2 just to make it, yeah? So for petrochemicals, all these polymers, just what we call the scope 1, scope 2 emissions is massive. Even for my bottom of the barrel bitumen, that short residue fuel oil, even before you burn it, for each ton you're generating half a ton of CO2, yeah? So that's why, you know, the billions of liters of oil is generating gigatons of CO2. So that's what it's doing. And it's controversial because the biorefinery is not flavor of the month in America because they already have a lot of corn, this, that, and the other. So they've already got a strong lobby into bioethanol and stuff like that. So you had a second question?
Yeah, the second question is, sorry if it sounds a bit provocative. You started off by saying that the aim is to reduce the CO2 emission. And all these interfacial techniques which you described is basically aimed at how to extract oil better from porous rocks or sand or whatever it is.
Yeah.
So I see a disconnect between these
what
two.
I'm hoping, we've done all that, right? So everything about production we know. What I'm hoping to use, and it's not a provocative question, it's exactly what I would want, is to use what we have learned in the oil and gas, but for sustainable technologies. So for generating green hydrogen, where as long as that delta V is coming from renewable source, the colloid science is there, and for biorefineries. So that's where I think there is really untapped opportunities. And that's where it's controversial, but you would think we have a lot of experience in oil and gas at scale. I think some of that can be tapped for sustainable energy routes, yeah? A lot of people think the techniques, the fluid flow, we used to be the gods of fluid flow in Shell, right? We're not so much now, but the flow is so important to us. So anything which requires flow, wind energy, solar, less, where we can help. Bio for sure. The reason we're quite interested in bio is it's so close to our skills. It's so close to our skills, and it's not fossil, yeah? But it's an excellent question. We ask ourselves that question quite frequently. Yeah? Any other questions on anything industry related or anything, really?
Oh.
So that oil spillage onto the sea, so can some of these
Yeah,
techniques
so
be used?
when we had the Macondo, well, not we, that was BP, not Shell, please. But when that happened, there was a lot of discussion about using surfactant solutions to fix it. It's very controversial because it's a bit like what happens when we do chemical EOR. How do you separate the oil from the water, which is now a microemulsion, right? Or not micro, but an emulsion, very stable. And what happens when those surfactants get into the water. So I think what we're trying to do, not let that spill happen in the first place, easier said than done, but we have to tighten up on that. And then I think they just try to get mechanical, so you'll see those beams. They'll try and put those buoys around it and try and stop it. But I would prefer to prevent rather than fix. Yeah, but there was a lot of work, and the surfactant science in that work was not done with a lot of rigor, personal opinion. It was quite often surfactant vendors selling you cocktails which are extremely expensive, and I'm not sure how, I'm dubious quality, yeah, in terms of cleaning or resolution. That's my, yeah, it's recorded, right? So that's my opinion, not Shell's opinion.
I have one question. These surfactant molecules are used for these industries, but there are some concerns that the surfactant molecules itself, they are also have some hazards in environment. So how do you tackle that?
No, they do. So you're all from Bangalore. So if you go to our lakes and every time it
Yes,
rains,
yeah.
now whether that's surfactant or not, I'm not sure. I think we do it relatively responsibly. I'm not too worried too much about the surfactant solution because that can get diluted away quite quickly.
Okay.
And if it's water soluble, it shouldn't get into your food. There are other things. There's something called eutrophication. So when I was growing up, the formulations were actually probably superior because they had something called sodium tripolyphosphate. So you'd have phosphate in there which would go and bind calcium. And calcium was bad for cleaning. And so those were very good performing detergents. Unfortunately, phosphate, when it gets into your water, into your lakes, it acts like a fertilizer. Okay. It is a fertilizer, right? Okay. And so what would happen is suddenly you get a lot of algal blooms and this, that, and that. Your bioavailable oxygen dies, and basically your fish die. Yeah. So they have banned all our formulations across the planet are now zero phosphate, and we use zeolites instead. So every time you look at a new formulation or a new ingredient, we try and go through. Everyone tries and goes through the effect on environment. Yeah. Is that being done with true rigor, and how well is that being happening? Debatable. The Europeans are a bit ahead of us, but sometimes you might argue they're a bit bureaucratic. The EPA is in its own tailspin in America, so I'm not sure how much they're looking at it. But we look at it in India as well. The BIS has these standards. And as I said, we got rid of the hydrophobic surfactant, even though it was good at cleaning, but because it's not sustainable. Yeah, so we look at it, and that's how you filter off. The bigger concern is that surfactant we use in all our formulation, even the non-ionic, comes from oil. All right. The only thing that doesn't come from oil is soap, vegetable oil. Unfortunately, so people in Malaysia are generating killing normal plants, putting palm down because the palm oil is good for biodiesel as well as for us, soap manufacturers. So there is, even when Unilever comes, they will ask you, what can I do instead of using soap? And that's the reason. So every single element of this challenge has multifacets on it, not just politics, economics, and it'll hit you in ways you can't imagine. Yeah. So it's quite fun that way. I would really encourage people to visit, the Unilevers and the Shells, their R&D, see what it's like. It's a lot of fun. Nothing like it.
Thank you.
so please do get involved. And please do join industry as well. We have too many people like me who talk the talk, who don't walk the talk. So please, please do. And if there are any questions about R&D in industry in general, feel free to contact me.
Any questions from the students about
Yeah.
R&D in the industry or anybody else?
I would encourage, even if you can't get a project here, speak to Unilever for internships and stuff like that. So you see how we do projects in industry, 6 months, 3 months, if it's allowed by RRI. It's an eye-opener. We used to do that in Shell as well. At the moment, Shell might not be looking, but it will be fantastic for the students to see that. Or get a project with Unilever to see how they do it. Unilever has a fantastic pedigree in surfactant science. So that boss who kicked my backside when I did that first wetting experiment, he was Rajesh's first boss as well.
I see.
So you just ask him about Peter Garrett. And for those of you who are doing thermodynamics, I don't know if you've ever heard of Redlich and Kwong equation of state. It's used throughout the planet. Redlich and Kwong were not academics. They were Shell engineers. So there's a lot of pedigree. Unfortunately, last 20 years, that pedigree has disappeared. But so we do some really fun stuff in industry. Nothing like it. When I did Vim Polycoat, the most exciting thing is you stand in a shop. It sounds crazy, but you speak to consumers who are buying your soap bar, the Vim plastic coating, and then asking them, how does it work? Do you like it? And when they give you a positive thing, which they did, the feeling you get is really nice, because that saved the brand. I'll just say a word about that. That Vim was in a downturn for other reasons I won't explain. But we came up with this idea of coating the Vim with a plastic coating so that water couldn't get into it, so it lasted longer. Before Vim plastic coating, we were at about 120,000 tons a year. It dropped because of a quality issue to 80. And within 1 year, we got it back to 120 and beyond without any marketing. Right? So you'll know Unilever, a lot of adverts. We hardly had any adverts for this, just on the quality of that product. Save the brand. What that means is factories are alive because of that innovation. So one of the best things, yes, meeting a housewife telling me how good the product is, but when you meet the unionized category in those factories who know what you did saved their jobs, they touched our feet. That's how important, because they stayed alive, at least in terms of salary, because of that innovation. So that's also something in industrial R&D gives you a kick, because all the factories are in villages. Yeah, they're not in Bangalore. They're all in villages, relying on HUL for survival. So
Okay.
if that gives you a kick, please do come to R&D in industry.
And you should also tell us about the peer soap, maybe over coffee.
Yeah, sure.
So let's thank Girish for a very interesting talk. And
Oh, fantastic. Ouch. Thank you. I'll see if they must have a picture of the bungalow. I'll see if the bungalow behind has. Did you ever visit the Malleshwaram in those days, in the early?